Hello students, this is Dr. DA and welcome to Chem 1B. This is going to be our first video lecture, so if you are here, I'm glad you found us either in your Canvas course page or in our YouTube channel. So we're going to start with a bit of a review and then we'll go on directly into the topic of this unit, which is chemical kinetics. Let's talk about chemistry for a little bit, things that you learned in the past. Chemical changes. Remember, it's a change where there is a change in the composition of a substance or more substances. In other words, you end up with a different substance than what you started with, as opposed to a physical change where the substances involved do not change in composition. Now, a chemical change may consist of one or more chemical reactions. Chemical reaction being a specific substance or set of substances called reactants interact to form a new substance or set of substances that we call products. Remember that a chemical reaction involves the rearrangement of atoms specifically, but not the creation or destruction of matter. In chemistry, we write chemical equations to describe the change that happens in a chemical reaction. So a chemical equation is like kind of like a chemical sentence in the language of chemistry. It's a symbolic way of representing a chemical reaction. So you might recognize something like this. So note that we have an arrow indicating the change. On the left of that arrow are the reactants. On the right of that arrow are the products. Notice that we also have in parentheses the physical state of each substance. In this case, G stands for gases. So what we want to do then is we want to make sure that we obey the law of conservation of mass. In other words, the chemical equation must be balanced, not by changing formulas, but by changing the coefficients, the numbers in front of these formulas. And this is what we have when we have a fully balanced chemical equation. Now, the description and application of the quantitative relationships between reactants and products is what we call stoichiometry. Another thing to review is that in looking at chemical equations based on the types of rearrangements that we note in the chemical equation, we can classify reactions into different types, right? So let's see if you remember what are some of the types of reactions that we classify. Okay, we have double displacement reactions, which include precipitation reactions, acid-base reactions, and many gas production reactions. And then we have another large category, the oxidation reduction or redox reactions, that include combination or synthesis, decomposition, single displacement, sometimes called single replacement, and combustion reactions. Okay, now let's start with three major questions that I hope we can address throughout the rest of this semester. Number one, will a chemical reaction take place? Number two, if it does, how fast will it go? Number three, when will the reaction stop? Question number one, will a chemical reaction take place, falls into the realm of thermodynamics, and we will address this in a later unit in the course. If the reaction does take place, how fast will it go? Well, that belongs in the realm of kinetics, which is the topic of this current unit. Question number three, when will it stop? We will study this in the context of what is called chemical equilibrium, which we will address again in an upcoming unit of the course. Okay, but the topic of this unit is chemical kinetics. Remember, we said thermodynamics is going to attempt to give us an answer to the question, does or will a reaction take place? But kinetics tells us, okay, let's say that the reaction does take place. How fast does a reaction proceed? We're going to start by describing or defining what is called the reaction rate. Reaction rate is the change in the concentration of a reactant or a product with time. So we can describe it with that fraction or that ratio there, molarity, over time in seconds, which is the unit we typically use. So let's consider a hypothetical reaction, reactant A being converted to product B. One way of describing the rate is by saying that the rate of the reaction is this, delta bracketed B over delta T. In this case, delta bracket B is the change in the concentration of product B over a time period delta T. Typically the concentration in molarity, the time period in seconds, typically. Now, look at this description of the rate. In this case, we are describing it in terms of delta bracketed A, which is the change in concentration of A, again, over this time period delta T. Now, notice something interesting in this expression, that negative sign. The idea here is that if we're going to have a unified expression of the rate, regardless of whether we are measuring the appearance of a product or the disappearance of a reactant, they should both give us a positive value for the rate. In the same way that when we measure the speed of a car, we say, well, it's going at 60 miles per hour. We don't say plus 60 miles or minus 60 miles per hour, regardless of how we measure it. So because the concentration of A decreases with time, we're going to put a negative on the delta bracketed A expression, okay? Now let's consider a situation where in this reaction, we're going to depict the molecules of reactant A in black and the molecules of reactant B in red. So let's say we track this reaction. You can see as red spheres are appearing here as B is produced over a certain period of time. Now, assume that you could actually measure the concentration of either A or B at any given time interval. We could generate a graph that looks like this. Notice that in the black curve, we see the decrease in the numbers of molecules of A, and in the red curve, we can see the appearance or increase of molecules of B over a certain period of time. So we could describe this as minus delta A over delta T because, A is decreasing, or we could express the rate as the appearance of B, so delta B over delta T. Now, one question would be the following. Number one, since both graphs are curved, so when we speak of the rate of decrease of A or increase of B, we're going to have to be considering more of an average since it is not constant over the time period that we are studying. Another question actually is, why does it seem like both curves level off? Well, we're going to see later on that as the amount of reactant decreases, the rate might also decrease, and this has to do with a model that we're going to present later on for how chemical reactions take place. Let's consider a reaction where we can actually see this color change. So here is the reaction of aqueous bromine with, this would be with what we call typically methanoic acid or formic acid, and it generates bromide ions, hydrogen ions, and carbon dioxide. Well, what is interesting about this is that the aqueous bromine or bromine, depending on how you pronounce it, is a red-brown solution. As the bromine is converted into bromide ions, we can see over time a change in the color of the solution as the red-brown color starts disappearing. Now, why is this useful? Well, you could describe this qualitatively and call the first beaker with solution here dark and the last one here colorless, and just make qualitative descriptions over certain time intervals. But in this case, we can actually quantify this by using a technique called spectroscopy. Now, in spectroscopy, if you remember, we know that the atoms that make up substances are set up in different energy levels. So this allows for transitions of these electrons into excited levels and for them to return to their ground levels. These transitions can be produced by the absorption of energy from light of specific wavelengths. So this is very useful for identification purposes because many substances have very unique profiles of absorption of light. Now in this case, since we're describing a change in a color that we can see, that means that we are talking about light in the realm of visible light, which is between 400 and 700 nanometers. In the case of the bromine solution, we know that it has a maximum of absorbance when light of 393 nanometers wavelength is kind of like shined through the solution. There is something called the Beer-Lambert law, which says that in essence, the concentration of the solution is going to be directly proportional to the absorption or the absorbance of light. So that means that since bromine has a bromine solution has a maximum at 393 nanometers, we can look at the spectrum at different times after the reaction has started and generate a graph like this. You can see that in the beginning there's a sharp distinct peak around a little under 400 nanometers, and then as time proceeds, T2, T3, which are later times, the size of that peak decreases. And so we can use a graph like this and correlate the actual absorption with the concentration of the reactant in solution, and we can actually generate a chart or a table that looks like this. So here we have at different time intervals, what is the concentration of bromine in that aqueous solution. And remember, we obtained the molarity of the bromine by converting the absorption at 393 nanometers into units of moles per liter. Now, what does this look like when we turn it into a graph? It looks like this. So you can see how, yes, the concentration of bromine decreases as it is being converted into bromide ions. However, it is still a curve. I'll explain those little triangles later on in our next slide. So one of the things we could say is, well, what if we assume that over this interval, we can approximate that relatively, not too sharp changing curve here, and we can approximate it as a line. So we could describe what is called the average rate. In other words, the minus the change in the molarity of the bromine over a period of time. And so we can basically pick 2 points on the graph and take the final minus the initial concentration over the final minus the initial time. Of course, we would try to pick a short interval here so that over that short interval of time, we could say that the curve actually approximates a line. And so what we're taking really is a straight up average rate and average change here. So this is what we call the average rate. This is the change in the measured concentrations during any particular time period, and we do this by a linear approximation of the curve. In other words, by choosing an interval over which the curve looks like a straight line. However, the larger the time interval, the more the average rate deviates from the actual instantaneous rate. What do we mean by that? Well, the instantaneous rate would be the change in concentration at any one particular time. In other words, we would pick an actual point on the curve and calculate the slope at that point. How do we do that? Well, we determine the instantaneous rate by taking the slope of a line that is tangent to the curve at that particular point. This would be actually the first derivative of the function for all you calculus fans. In other words, this would be, the molarity over dt. In other words, the change in molarity over a very, very, very small change of time. So let's see what the graph looks when we do that. Okay, here's the previous slide, and now what we've done is we've picked 3 points, right? 100 seconds, 200 seconds, and 300 seconds. And we've taken a tangent through that point, and we have, using a right triangle, we can calculate the slope there. And this would be what the instantaneous rate is. It would be the rate, that is, the slope of the tangent for a specific instance in time. Now, notice that, of course, when you look at the numbers, you see that it changes, right? Because it's a curve, we are actually seeing that the instantaneous rate is changing as time progresses. Let's put this on the screen here, so you can see how at 100 seconds the slope of the tangent is 2.96 times 10 to the negative 5 molar units per second, and then it changes at 200 seconds, and it also changes at 300 seconds. Feel free to stop the video at any time and go back and make sure you understand this difference between the average rate and the instantaneous rate, okay? Feel free to do that. Now let's see what the data would give us. Let's say we repeat this calculation of rate for every single data point. In other words, we calculate the instantaneous rate. Now let's plot the rate calculated this way versus the concentration of the bromine. Not the time, but the concentration. Voila, we get a straight line. Your data now fits a straight line. And a straight line is very useful because it tells us that the relationship between the property on the y-axis, which is the rate, and the property on the x-axis, which is the concentration of bromine, is a direct proportion. Rate is directly proportional to the molarity of bromine. If we change this into an equation, we would say that rate equals K, some kind of constant, times the concentration of bromine. Let's rearrange this equation and find that K equals rate divided by the bromine concentration. And we're going to call this property the rate constant. And if we calculate that for any one of these data points, we find a very consistent value. In other words, it's very, very little change. As we expect, it is a constant. So if we take the average of all these different calculations of K, we get a value of 3.50 times 10 to the negative 3 s to the minus 1. And some of you might be scratching your heads about what that means. Well, let's go and check out how and why we got these kinds of units and what that means, okay? I'm going to go to my document camera to explain this, and then we'll take a little break and proceed to our next section. Okay, so the question we want to address here is, how did we get the units of the rate constant? Remember, we started out with an equation that said that the rate was going to be equal to some constant K times the concentration of the bromine solution. So if we can rearrange this, we would say that then K equals the rate over the concentration of bromine in solution. So let's see what the units of this are. We've said that the units for rate are the molarity change per second. And of course, the concentration is expressed in units of molarity. So that means that those will cancel out, and so the rate is going to end up with units of 1 over s, 1 per second. In other words, the reciprocal of the seconds. Now, what we can do here is apply something that we should have learned in algebra, which is that whenever you have an expression such as, let's say, the reciprocal of some number to some exponent n, we can also write that as a to the minus that particular exponent. And so, for example, density, which is typically expressed, let's say, in grams per cubic centimeter, right? We could show that as grams times centimeters to the minus 3. And that is exactly the same. So therefore, we can express the units of K in this particular instance would be either 1 over S, or, because sometimes in a word processor it's hard to insert fractions, we can express it as S to the negative 1. And that is how we got the units of the rate constant in this case.